Okay, so it's our pleasure to introduce our most local speaker, David Nadler, who will tell us about the pair of pants.
Great. All right. Thank you very much for the opportunity to speak. So yeah, so there were a couple of different talks that I was kind of debating giving. One of them was even suggested by one of the organizers, but I decided to buck the organizers and gave a different talk, which I hope will sit well. Okay, so I'm going to talk about pair of pants. So the official title is Wrapped Microlocal Sheaves on the pair of pants. And so I'm going to remind you, I'm going to start the talk by reminding you and telling you something which many of you know very well and I only have learned recently, which is what are pants. I'm going to spend some time talking about pants, which are very interesting. Well, anyway, I didn't know pants were so interesting. The second part will be about what are wrapped microlocal sheaves. So let me just say maybe the name conveys, so there's a kind of growing dictionary between Fukaya categories, Fleur theory, and microlocal sheaves. And so I'm going to explain how to add one more entry to this dictionary. So there's a version of the Fukaya category called the wrapped Fukaya category. I'm going to explain a kind of wrapped version of microlocal sheaves, which is a kind of appropriate object to think of in this situation, because what we want to do eventually is we want to do mirror symmetry, homological mirror symmetry for the pair of pants. Okay, so I'm going to, I don't know how far I'll get, but I think that's some sort of outline of what's going to happen. Okay, so these two can be largely understood independently. So I'm going to start with pair of pants, which is kind of very concrete. Draw a lot of pictures, explain what this is doing here, and then shift gears and explain this kind of A-brains, wrapped A-brains from the perspective of sheaves. Okay? Yeah, so I think we'll hear, maybe Harold will talk about microlocal sheaves tomorrow, so I hope that any kind of act of violence I do to microlocal sheaves won't deter you from Harold's talk. Okay, so, great. All right, let me start with what are pants. I'm just going to present it in a way that's kind of tuned to what we'll say later. So let's take CP n plus 2, so complex projective space. I see I've already, let's do CP n plus 1. So we'll just have coordinates z1 through zn plus 2. And then let's write hi inside of here for zi equals 0. Okay, so for one of the linear hyperplanes. And then let's write h0 for a generic hyperplane, which we'll take to just be z1 all the way up to zn plus 2 equals 0. Okay. So, and now the pair of pants. Definition, pair of pants of dimension n is what we get when we look at h0 and remove its intersections with these hyperplanes. Okay, so it's h0 minus the union over I of the intersections of h0 with h1. Okay. So now, of course, h0 itself is just a projective space of one dimension less. So what we're doing here is we're just taking projective space and removing taking n-dimensional projective space and removing n plus 2 hyperplanes from it.
Your second line should say CPn plus 1.
This should say, thank you. Yes.
The second line. The one
No, this one. No, sorry, this one. Okay, so my n's n plus 1s and n plus 2. Yeah, so I should say one of the reasons I wanted to give this talk is because I'm finishing writing a paper about it, and one of the catastrophes in the draft is n's and n plus 1s and n plus 2s. Okay, so, okay, yeah. So let me just. So it's the complement complement of n plus 2 generic hyperplanes in CP, CP n plus 1. Okay.
It's CPN.
And CPN. Thank you. CPN. Okay. Sorry. Yeah. So great. Everyone's playing along. All right. So let me just draw a picture. So here's CP2. So CP2 has you know, H1, H2, and H3, and then H0 is this guy. It's H0. Maybe I should enjoy these colors. Are they erasable? I don't know. So here's H0, and when we remove these intersection points, we see that we get a line minus 3 points. So you know, for n equals 2, n equals 1, P1 is CP1 minus, say, 0, 1, and infinity. Okay. Okay, I find it very useful to remember also, just to check your reality, that P0 is a point. Okay. And I'll explain, this is going to have something to do with n equals 2. Okay, so what, yeah, maybe I should do this kind of thing once or twice in the talk. So, of course, this picture, if I were to, you know, draw it like a topologist rather than an algebraic geometer, I draw it like this, where these 3 points are the 3 removed points. Okay, so this is a picture of P1. Okay. So now I'd like to catalog structures on the pair of pants that are going to be relevant to what I'm going to talk about. Okay, so I have a list of about 4 or 5 that are all, I'd say all until the end, are well-known standard structures, but like I said, I learned a lot of these somewhat recently, so anyway, I'm enthusiastic to list them. Okay, so structures. Okay, so the first is that there's an evident Cn plus 2 action on Pn, just coming from permuting the coordinates and the fact that the equation is invariant. So, okay, so this is an important structure, and let me just say everything I'm going to say is going to be invariant under this structure, or at least until the very end, everything I'm going to say is going to be invariant. And for those of you who are already bored, you can kind of daydream what this has to, what this has to do with sigma 4. Okay, so, all right, so that's the first structure. The second structure, which I'll just say kind of informally, is that there's a kind of inductive structure near infinity. Okay, so I don't want to be too precise about this, but I just want to give you a sense that the part of the pair of pants that's difficult is the part that sort of lives in here. The ends of the pair of pants, if you already understood the previous pairs of pants, have the following form. So the Pn ends, this is informally, look like Pn minus 1 across C star. So it's just an informal statement. But you can see, like in this picture, that each of these ends looks just like a point across C star. Okay, and then something interesting happens in the middle. Okay, now this is something that we could study the A model or the B model of, and those are in some sense the 2 different talks. So I'm going to take the point of view, I'm going to try to understand the A model of this. So I'm just going to point out that this is naturally a Stein manifold. It's you know, an open, it's an affine variety, so it's a Stein. So in particular, it's Weinstein, and in particular, it's a Louisville manifold. Okay, so I'm going to be interested in the exact symplectic geometry. So I'm going to be interested in the exact symplectic geometry that these words tell me is kind of tame enough that I won't go into some sort of craziness. Okay, the next thing is the kind of amoeba or tropical picture of it. So this is going to look a lot like what Melissa drew in her talks, and kind of not coincidentally. So let me just remind you that we have a moment map, or a log map, maybe I call it moment map, from CP n plus 1 to R, well, I guess, let me write Rn, maybe naturally Rn plus 1, but let me write Rn. and its image is an n simplex. Right. This. Okay. And now, so for example, for n equals 1, we see the usual 2 simplex. And now we can look at the image of the pair of pants under this map, and its image is some kind of amoeba-like creature. Okay, so this is mu of u1. Okay, so this is the amoeba. So the amoeba equals mu of the pants. And inside of the amoeba, there's a kind of, I guess amoebae don't have a skeleton, but inside of the amoeba anyway, there's a kind of a spine here, which is kind of the kind of tropicalization of the parapets. Okay, great. So, all right. So this is kind of, I think, very, very well-known background, but now I'd like to sort of start on something that's maybe less well-known, although I'd be very interested to hear the experts weigh in. So that
in this, what about this geometric setting has made you decide to extend the skeleton to the boundary?
Oh, I didn't even say the word. I didn't say the word. Did I say the word skeleton? Maybe I said the word skeleton. I mean, I just drew kind of the most naive, natural thing that I would draw, given a kind of given the desire to combinatorially organize this kind of funny amoeba. I drew something natural. I don't know. I'm not going to use this. I mean, all the proofs will use this kind of a picture, but like you can kind of just put that aside for the time being. Okay, so now I'd like to talk though about skeleta. So I'd like to talk about Lagrangian skeleton, okay, which I'll call Ln inside of Pn. So let me just remind you roughly about what I mean by a Lagrangian skeleton. So when we're in the setting of, say, a Stein or a Weinstein manifold or Louisville manifold, we can pick some kind of exhausting function and then look at the stable set of that function and get a kind of core or skeleton that in general will be isotropic, but here it will be Lagrangian. And it's everything homotopy retracts onto this core, and there's some, well, okay, so the symplectic geometry retracts to a neighborhood. And let me just say as a kind of philosophical point of view for me, what my goal in a lot of trying to understand this kind of geometry is I'd really like to let go of the symplectic geometry and just understand it in terms of combinatorics of the skeleton. So that's sort of, this is an example of that kind of game. So trying to understand symplectic geometry just in terms of the combinatorics of the skeleton. Okay, so with that in mind, let me tell you what the most natural skeleton is. So there are many different choices, but there's a most symmetric choice, which I'll call Ln, which will be this. Okay, so let me explain what I mean. So inside Rn, there's something called a permutahedron. So Ln, let's let Ln be what's called the permutahedron. So this is it's an n-dimensional polytope. Sorry, n plus 1 dimensional polytope, and it's hooked up directly out of the symmetric group. You essentially take a kind of generic vector and act on it by the symmetric group, and then take the convex hull. Okay, so it equals the convex hull of the symmetric group n plus 2 acting on a kind of generic vector. Okay, so let me draw it in a couple of examples. So for, well, let me just draw it in the case n equals 1. Yeah, n equals 1, it's just a hexagon. Okay, so this is L1. Okay? So I brought this because this is L2. Okay, so this is what you get if you take, well, okay, so it's 3-dimensional. So Ln is n plus 1 dimensional. So this is what you get if you take 4 generic vectors, say their sum is 0, and then you, yeah, maybe I should have written generic vector, one generic vector. Yeah, one generic, okay, maybe I haven't written exactly what I should have, but in any case, this is the permutahedron. Let me write something more kind of mathematical here, just so that in case anyone's playing at home. So this is just, sorry, maybe I think I maybe am off by an index. Let me just write what I have in my notes. So it's the convex hull. Yeah, the problem is my notes had n and n plus 1s and n plus 2s, all different. Sigma n. Okay, let's see. This is called P2 in my notes. So you tell me. Okay, so up to n, up to a choice of n, I should do something like. Okay, so can you guys tell me? Is that will that be
That one's right.
That one's right?
Yeah.
Okay.
My opinion.
Okay, so up to a choice. So if n equals 1, no, I think I'm.
No, I think that one's right because it sits in a plane of codimension 1 inside Rn plus R. Right?
But it should be dimension n plus 1, so I think there should be a 2. I know better than Tabaku, but I'm going to try.
I see, so you're using not the convention units.
Exactly. Exactly. Okay. Okay, so here's the next one. Okay, and so one of the amazing things about this guy is that he tiles Rn plus 1. Okay, so this guy, there's a tessellation of Rn plus 1 by Ln translates. Okay, so there's a natural lattice. I'm not going to write it down, but there's a natural lattice. So that if you take this guy, well, you guys would know well that if you take the hexagonal So I find it hard to picture how it works with this, but if you go online, people have beautiful pictures of growing. I don't know whether. Okay, anyway.
You have more pieces, maybe set the.
Yeah, well, I was desperate. I ran out of pieces. Yeah, these two are not like some symmetry breaking. There'll be symmetry breaking soon, but these are just not enough pieces to make it. Okay, so all right. So here's the first proposition, which again maybe is well known to experts. I'm not sure. So let's take this guy and look at all his translates, and then quotient out by the lattice. Okay, so sorry, let me write rather. Okay, so let's set definition. Let's set Ln equal to, I don't know exactly how to write this, but sort of Ln mod translations. Okay, so that's not mathematics. We don't write something that's not invariant under translations mod translation, but I hope you know what I mean. So what I do, yeah, sorry, let me actually take the boundary of this. So the boundary of Ln modulo translation. So in this picture, the boundary would be just, of course, this. Okay, which then forms a kind of lattice mesh in the plane. Okay? Or you can imagine just this two-sphere and then translates of this two-sphere all around. Okay? Okay, and the first proposition is that, okay, I'm not explaining how, but that there's an embedding of Ln into Pn as a Lagrangian skeleton. Okay? So, so let me draw some more pictures. Okay, so what happens in the case n equals 1? Okay, so for n equals 1, this is very, very well known. Yeah, oh, sorry. Well, okay, at some point I should start listing people whose papers I've learned things from. So let me, yeah, maybe, okay, so just a moment before I draw them. Let me just say that there's a group of people, some represented here, whose work is I've really learned a lot from. So there's first Paul's paper about the case n equals 1, and then Nick Sheridan's generalization to all dimensions, and then a paper of Abu Zaid, Aru, Markov, Zarkov, Orlov. Good? Okay. So anyway, these 3 papers have helped me a lot. And in some sense, what I've been trying to do here is understand what's in them in a kind of more elementary way. Okay, so let me draw the case n equals 1. What's going on? So for n equals 1, here's our pair of pants. And then our skeleton is going to be this hexagon, but the hexagon gets kind of rolled onto itself. So this hexagon under translations has 2 different points. These 2 points can't be identified under translations, so they correspond to, say, one in the front and one in the back. And then it has 3 different edges, say this one, and this one, that link those 2 points. So the kind of boundary of the hexagon gets wrapped around the pair of pants, and it's a skeleton in the naive sense that it's the whole thing homotopy retracts, but also all of the symplectic geometry is captured by a small neighborhood of the skeleton. Okay, so this proposition is saying that in higher dimensions you can take these permutahedra and do the same thing. So, okay, I won't try, but you can imagine translating this all around, and it gives you some equivalence relation on this permutahedra, which gives you a space which generalizes this picture. Okay, so
Can I ask how many points does the quotient have?
you can ask, and I can tell you, but I don't know if I can tell you. I mean, okay, it's like some, you have to access a different part of the computer. Let's see. Okay, there are a bunch of 2 to the n's and 2 to the n minus 2's and things. I mean, yeah. I mean, everything you want to know about this was known to like Postnikov and when he was born. I don't know. So there's lots of.
There's lots of vertices of this quotient.
Yeah, I mean this is kind of growing. If you mean like is the growth rate is going to be. Okay, so I'm sorry, I don't just know the initial numbers, but maybe like 2, 14. I don't know. The growth rate is big. Okay, so.
Sorry, in this n equals 2 case, is it some genus 2 surface attack, some disks and so on?
Yeah, so this thing, yeah, I should say, all right, so I'm very interested in the combinatorics of this, but if you were just interested in the topology, you could turn this, you could just kind of smush this thing into like the boundary of a cube. Okay, you could decide, I mean, this is something, I don't think we'll have time, but that kind of symmetry breaking is important. And you could smush this into the boundary of a cube, and then what I'd be telling you is take the boundary of a cube, and then take its identifications under translations. Okay, and that's homotopy equivalent, or I mean, homeomorphic. Well, you have to be careful about how you do it, but that's yeah, homotopy equivalent to this kind of picture. So you're just taking an n-torus, removing a kind of an open ball in the middle. I don't know if you think of an n-torus as a cube with translation identification. You're removing the interior, and then looking at all the panels and rolling the panels. But so what I want to advocate, I'm gonna not go to this immediately, maybe later in the talk, but what I want to advocate is that in some sense I claim that once you have this, you're done. I mean, that you can calculate anything you like, modulo foundations and analysis that I don't want anything to do with, but the point is that I think there are a lot of models now for A-branes, so I'm going to talk about one called microlocal sheaves, but there are other models out there that once you get to this point, let me just make the comment, kind of a note or a remark. So this, so Ln inside Pn has what you could call arboreal singularities, or what I like to call arboreal singularities, which is a kind of very nice combinatorial class of singularities for which you know what categories of A-brane should look like. Okay? So it means that once you're in this situation, you can make any calculation you like, and I could give a different talk at this point. I could not tell you about microlocal sheaves, and I could just tell you now how to identify this with its mirror Landau-Ginsburg model, just using the kind of combinatorics. And it's a very beautiful picture. It involves considering like constructible sheaves on this kind of a picture. It's very elementary, beautiful, but I think there are situations where getting it to a combinatorial picture like this is much harder. So of course it's good to have kind of general tools like microlocal sheaves. So the fact is we know microlocal sheaves in this situation have a very clean form, but it's good to have the general tool nonetheless.
Oh yeah, so I feel like, so it seems like this is like coming at least partially from this like symmetric group action on PN.
Yeah.
So like what in general do you need? Like is there any like general property of the space with the symmetric action plus something else that gives these skeletons?
Oh, sorry, this skeleton, if you like, comes from much, okay, maybe, I don't know how to say it just like you have a symmetric group action, so therefore you get this. The way I think of this skeleton is a little bit, I don't know, people say like this, it's a little bit like scratching your left ear with your right hand, but I think that's just because of my limitations. But this skeleton comes from thinking about, going all the way back to like Stein structures and thinking about Morse theory and assembling this thing from cells. So if I get to it, I'll talk about it at the end. So I kind of went down into a valley of confusion, and then Sheil Ganatra explained to me some aspects of this amoeba picture, which helped me a lot. So I claim you will, okay, if you're me, you'll start studying this, and I think this will come out the other. But I don't know how to say it just like you have a symmetric group action. Okay, so so I wanted to just say this because now I'm going to kind of move to the second half of the talk, so to speak. I'm going to talk, or second third of the talk, I'm going to talk about microlocal sheaves, which I think is a good general tool to study abranes. They're equivalent to Lagrangian branes in a lot of situations, and they have a lot of nice properties. But I want to emphasize, I'd be very happy to talk to anyone, that for me, in some sense, this is like, can be thought of as like the end of the story, because it's not difficult to match this up with a kind of V model. Okay, so now you can kind of forget the, oh, maybe I want to say one more thing about the pants, which is like in Melissa's talk, they appear as kind of the basic building blocks. So I'm not going to talk about general hypersurfaces in toric varieties, but of course that's kind of the point here. And I think once you understand these, there's a lot of, well, okay, it's not difficult to go further. Okay, so we're going to shift gears now, and I'm just going to give you now a primer on microlocal sheaves, because I presume that that's not something many of you have thought about.
Actually, there's something I don't understand about the sort of
Great.
the strategy here. So,
Yeah.
my understanding, the original point of the pair of pants
Yes,
was that you can degenerate anything to any open hypersurface to something glued out of pairs of pants.
that's right.
But you're analyzing the pair of pants using a smaller building block.
Yes.
So why is it interesting for you to degenerate to pairs of pants? Why not just degenerate arbitrary thing all the way down to the smallest building blocks?
Because I understand. I mean, yes. I mean, so the picture that I have, maybe it's the wrong picture, but is to go in like two steps. So you take the variety in the gross, I don't know, and you degenerate it to pairs of pants.
Yeah.
Then you need to understand the pairs of pants.
Yeah, but I mean, I thought the previous story you had to stop at the pairs of pants because from the point of view of symplectic geometry, there's nothing smaller somehow that you could break it into. But from the point of view of your geometry,
Oh yeah, there's some.
you could break it all the way down. So why,
Yeah, I mean,
why is the
you
pair
could.
of pants
I think
distinguished?
symplectic geometers can think, of course, about this thing as being built up of a trivalent node. I mean, people do. It's not.
May I paraphrase this by saying actually this is the smallest example where you see the full assembly rule for how to put together whatever smallest building blocks you might have, which might be smaller than that, but the way to assemble them that you will need to see a general example will involve the same complexity as this.
Let me mention an important kind of. All right, I'm not going to get to the third part of the talk, but let me mention an important thing. What would you do if you needed to glue this to another pair of pants? I don't know. Someone wanted you to glue this. What would you do? And what you need, but one very beautiful thing you can do is do some symmetry breaking, which is very useful for other reasons. You can take this pair of pants and make it look, for example, like this pair of pants. You can take this skeleton and make it look like this skeleton, and then glue together kind of a skeleton that looks like this over here, and then forget that you ever moved this guy around. So there's lots of moves you can do with the skeleton to kind of stretch, I don't know about the medical analogy, kind of stretch the skeleton in various directions to glue together. So this calculation that you understand the skeleton is kind of not sufficient, but if I were to get to the third part of the talk, I'd explain how to do these kinds of moves, which I think are, is sufficient.
Would this be a homotopy push-out?
Sorry, of what? Oh yeah, that's right. So eventually, all right, so I'm now going to talk about microlocal sheaves. And so they have some, if you use that model as A-branes, they have a kind of formal property that, they are calculated as a colimit on big spaces. Okay, so, all right, so now let's forget pair of pants, and I'm going to just talk about microlocal sheaves for a little while. Okay, so I'm going to try to kind of give you a primer from the start. So I don't know how it will go, but let's see. Okay. This is going to be a kind of intro to microlocal sheaves. And my aim in particular is to get to this notion of wrapped. I mean, that's sort of everything I'm going to tell you, I should say, is everything about microlocal sheaves is from Kashgar and Shapira. So they did something remarkable, which is like before, I don't know what, there's some analogy, before the world knew they needed a widget, they produced like, an amazing widget. So, okay, so anyway, so everything I'm going to tell you is due to Kashgar and Shapira until at some point I'm going to try to tell you about a version of this theory that's called wrapped, that I think is a very important version of the theory, just like wrapped Fukaya is an important version of the Fukaya category. Okay, so let's get started. So X is a real analytic manifold. T star X is its cotangent, and I'm going to think about this with the usual exact symplectic, so conic exact symplectic structure. And okay, so now by the word sheaf, just for this talk, but I advocate this in general, I don't know, I'm going to mean a complex of sheaves of K vector spaces. The K is some field. The K is immaterial. I mean, everything I'm going to tell you could be done in kind of crazy generality depending on your taste for homotopy theory. Such that I want the following tameness. I want that there is a stratification. Okay, so I want to assume that there's a stratification S of X such that the complex, such that the cohomology sheaves of the complex restricted to each X alpha are locally constant. Okay, so, and then of course I want to consider a DG category. So definition, I'm going to write sheaves diamond on X to be the DG category of sheaves.
Draw for real analytic?
Sorry?
Draw for real analytic.
Yeah, that's right. Sorry. Yeah, strata or real analytic. I mean, you can do this in many different contexts. Semi-algebraic. I mean, there's all sorts of different contexts. This is what I want. I don't want you to allow crazy spirals or crazy sine 1 over x's. Okay. Okay. The diamond is here. So why the diamond? So the reason the diamond is here is because I haven't put any control on the size of the complexes. Okay. So no bound on the size. Okay, so I'm allowing myself to have kind of giant complexes, but they're still objects that are somehow manageable. They're not objects of analysis or objects of I don't know what. They're objects of combinatorics in a sense because they're locally constant along the stratification. Okay. Okay. Now
not bounded from below, not bounded above.
they're not bounded at all. Okay, so on a point, sheaf diamond on a point is just a DG category of K modules. Okay? So, I mean, that's not the object we want to study, that's kind of giant, but okay, we'll get there. Or, well, maybe we won't, but let me try. What time did I start? I started at 45? Okay. I go 45 to 45, right? Okay, great. I mean, not great, but anyway. Okay, so let me explain now why do these objects appear in a talk about symplectic geometry. And the point is that you really shouldn't think of these objects as living on X, you should think of them as living on the cotangent bundle of X. Okay? So in order to make sense of that, we need a notion of singular support. Okay, so the singular support of one of these guys is going to be a subset of the cotangent bundle. Okay, so this is called the singular support. And it's, among other good properties, it's closed, conic, and Lagrangian. Okay? Unless, I guess, if the sheaf is 0, then it's empty, which I don't know if that's Lagrangian or not. Okay, and it knows about the classical support, because if you intersect it with the 0 section, you just get the classical support. Okay, so this is some kind of version of support okay, so maybe let me try to explain, because that'll be important later, just at least in a cartoon, how you do this. Okay, so here's a kind of a cartoon of this support. So here's X, okay? And say my sheaf is constructible with respect to this stratification. Okay, so there's a picture of stratification. And now you're interested in some covector, say this covector. Okay, so this is the, I don't know, XC. This is some covector in the cotangent space, and you're interested in asking, does my sheaf have support at this covector? Okay, so the question that the test thing that you do is you take a small ball around X, okay, and then you pick some function whose 0 at X and whose differential is C, and then if your covector is not kind of generic, you have to say something about the quadratic part, but let me just ignore that. But you basically look at the cohomology of your sheaf on this ball relative to the negative half space involved. Okay? So you make that cohomological calculation. If that cohomological calculation is always 0, your sheaf is not supported at that point. And the support is the biggest, smallest closed set that is the complement. I don't know. It's the usual U of A. Okay? So it's easier to say what's not in the support. Okay? So that's the notion of singular support. Once you have this, maybe I should just maybe do it just to say an example. So let's say we have y inside x is submanifold. Then if I look at the constant sheaf on y, then the singular support of this is the cotangent, conormal bundle to y in x. Okay. Okay, so now once you have this notion of singular support, you can construct a symplectic invariant called microlocal sheaves. So, let's fix now lambda inside t star x. This is our skeleton. Okay, so what I mean is think of the formal properties that you like of a skeleton. So it's Lagrangian, it's conic, it's closed. Anyway, this is the kind of guy you want. So it's a closed, conic, Lagrangian. Okay, so this is where you're interested in having your sheaves supported. Okay, and let's also fix omega inside t star x, a small conic neighborhood of a point. Say lambda inside lambda. Okay? So now I'm going to make a definition of microlocal sheaves on this omega. So let's define microlocal sheaves, and I'll put the diamond here just to convey that I'm not imposing any condition on their size. Microlocal sheaves along lambda on omega, okay, is going to be the following. So I look at, let's take B to be the image of omega inside the base, okay, and I take sheaves on the base. Okay, well let me write something and then I'll say what I mean. And I look at a quotient category. So I'll say what I mean in a moment, right? Okay. So what do I mean? So this is going to be the category of sheaves so that the singular support intersection with omega is inside of lambda. Okay? And these are going to be the ones with no singular support inside omega. Okay, so in other words, I quotient by any sheaves whose singular support misses omega. Okay, so I don't know whether it's useful to put up such a definition, but I feel like at some point one really wants to know what is someone talking about when we're talking about microlocal sheaves, and this is it. Okay. So now let me tell you some formal properties that make you think this isn't just some ad hoc definition, okay? So I'm going to tell you that some formal properties that Kashiwara-Shapiro's theory of contact transformations tells you, okay? So, so maybe I'll list 3, okay? So good properties. Okay, so the first property is that this is a symplectic invariant, okay? So this is an exact symplectic invariant. Okay, so one of the most interesting parts of the story is to what extent is it really an exact invariant and not just a symplectic invariant. But let me just leave it at that for the time being. Okay, so Kashiwara-Shapiro proved that if you do contact transformations, you do conic transformations of such omegas, you will get equivalences. Okay, so this guy, while you think it depended on thinking of it as a cotangent bundle, it didn't. Okay, I mean it did in some maybe in some when you worry about coherences. So let me just say you're careful about coherences for those who are like really interested, but there's some very subtle things happening. But in any case, it's a symplectic invariant.
So why do you have to be careful?
Oh, because you might have said, all right, you really say it's an invariant, then I can look at like a circle of symplectomorphisms and come back and get the identity or something like that. Like, I'm trying to convince you that this didn't depend on its presentation as a cotangent bundle. But you have to be careful. Like the grading depends on its presentation as a cotangent bundle. Okay, Okay, second property is that it's the stalk of a sheaf of DG categories along lambda. Okay? So I told you, sorry?
Just so I understand, by property 1 you mean something like contact isotopy acts.
Yeah, I mean if I give you an exact equivalence between this and another open ball in a cotangent bundle,
Okay.
it will give you an equivalence of these categories. Or if you, yeah.
But you're not demanding it be an exact conic equivalence?
Okay, but we can have a discussion on what exact means, but conic and exact are sort of the same amount of structure. Okay, and then the third one is just that if it's the stalk is equivalent, not canonically, but at least equivalent to modules, DG modules over K at smooth points of lambda.
So after 2, you mean this is a global section of a sheaf of DG categories along?
No, the way I told it to you is I told you to take a small conic neighborhood around a point. So at each point, this is a definition of a category. And now I'm telling you that in fact there is a sheaf of categories so that these are its stalks. Okay? So there is not a, let me give you a kind of, the standard thing to be concerned about. If I give you this kind of a front projection, you will be able to construct microlocal sheaves here, 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 and so on using this definition. But you will not be able to construct, there are interesting global microlocal sheaves that won't come from global sheaves. Okay, so it's really happening in the symplectic geometry, not in the kind of polarized symplectic geometry. Okay, so
And what did you write underneath that in number 3, underneath the equivalence?
not canonically.
Oh, yeah.
Not canonically. I mean, this is something everyone who's thought about A-branes knows is that near a smooth geometry of A-branes is not interesting. I mean, it's just algebra, but of course there's lots of things. Okay, so let me just remind you of one standard calculation in the subject that convinces you this is not, that convinces you that someone at a neurosymmetry conference could be talking, should or could be talking about this. So here's the kind of standard example. So let's look at x equals S1. So T star x equals a cylinder. So here's the cylinder. Okay, so I'm going for the kind of easiest thing here. And let's take our Lagrangian. I don't remember my colors, but I think my Lagrangians were blue before. Okay, so purple before? Maybe the pair of pants was blue. Okay, anyway. Okay, so here's lambda. Okay? And now it's a good exercise, if you haven't digested this kind of thing before, to prove that microlocal sheaves on this lambda, on T star S1, are equivalent to quasi-coherent sheaves on P1. Okay, so this kind of a mirror symmetry. And you also will see that it's compatible with, I should have drawn that, I guess, the mirror symmetry conference, so I should have drawn the picture like that. But it's also compatible with the well-known, if you restrict to the poles, that this has to do, I told you that there was a sheaf here, and if you restrict the sheaf to, this open and this open, away from the zero section, that is, so let's call this open omega. So if I restrict mu sheaf lambda to omega, there's a commutative diagram like this.
So David, when you say QCO P1, you don't mean DB, you mean like in QCO?
No, I mean QCO. I mean the DG category of quasi-coherent sheaves.
Yeah, but not DG enhancement of DB, but of in.
Okay, I don't know what the DG okay, I mean.
Because you want your complexes to be unbounded, right?
Yes, there's no bounds here. I mean, so the next topic, which involves the word wrapped, has to do with bounding. Okay, so I don't know. Have I lost everyone? I don't know. Maybe.
I'm confused about why this diamond is here. Was something false about the diamond?
Yeah. So So why is the diamond's here for the same reason that the Q is here? Okay. So things are big. I haven't told you any finiteness at all.
I mean, would I want them to be big, or would it be false if I raised the diamond and the Q? And
Well, okay, this is a good philosophical. I'll put down the chalk. I enjoy a philosophical discussion. I mean, do we want big categories or small categories? Now, big categories and small categories are there's a kind of dictionary going back and forth, okay? But if you're someone who likes this object, then you probably prefer coherent sheaves or quasi-coherent sheaves. Maybe I don't want to buttonhole you, but so I would prefer a statement here that had coherent sheaves to a statement here that has quasi-coherent sheaves. Now, in certain situations, like for P1, which is, say, smooth, I can recover a statement about coherent sheaves from a statement about quasi-coherent sheaves. But for a variety that's singular, I can't. So there's different statements that you can make, and your understanding of them, I claim, all has to do with whether you understand singular varieties, or non-proper, non-smooth varieties. That's where you see whether, it doesn't really matter whether you're talking big or small, that's where you really know whether you understood things or not. Okay, so I could have given you a picture here, and it would have corresponded to, say, some category associated to a singular variety, like a nodal curve. And then we would have had a real debate about whether I should have put QCO or INTCO. Okay?
Why didn't you give us that picture?
Great. Okay. So great. So here's the question. Okay. So let's okay. So maybe you've seen this picture before. It's called a pair of pants. Okay. So so here's a symplectic manifold, and let me draw a skeleton in it. Okay, so my colors are all screwed up. I somehow went back to blues and purples. But let me not draw this symmetric skeleton I drew before, because that's kind of awkward from a perspective of a tangent bundle. Let me draw the kind of asymmetric skeleton I drew before. Okay, so let me tell you how to think. So this is kind of an example, another example. Okay, so this guy, okay, if you just say, all right, I haven't told you how to think about this as a cotangent bundle. I mean, one way to think about it is, well, okay, it's almost a cylinder. I'm missing something, so let's pretend it's a cylinder, and then maybe in an extra dimension, it's exact. Okay, anyway, I don't need to tell you, but I'm sort of trying to apologize for skipping some steps here. So if you take microlocal sheaves diamond on this guy, where, I don't know, L, L1, P1, okay? This, you will prove, is the same thing as INTCO of, a nodal curve. I don't know what xy equals 0. Okay, and it's not QCO. Okay, so if you know this statement, you know what coherent sheaves are on a nodal curve, but you don't yet know what perfect sheaves are on a nodal curve. Okay, so I don't really care about big or small categories. So the point is not diamond, but the point is, how do I extract from, say, a category, things like perfect or coherent. Okay? And for those who, I'm going to run out of time, but for those who have thought about infinitesimal versus wrapped Fukaya categories, they know that there should be kind of two versions, one perfect and one coherent. So I'm going to explain that now for microlocal sheaves. Okay, so okay. Do this. Okay, so yeah, so let's get rid of the diamond. And again, the point is not necessarily because we don't like big categories, but because we really are interested in the difference between homology and cohomology, or the difference between perfect and coherent sheaves. Okay? So, sorry, just all the chalk seems to have shrunk. Okay. So, okay, so what we want to do is find I don't know, natural small categories inside U-sheaf, diamond, lambda, omega. Okay? Okay, so I mean this in kind of great generality. I don't mean specifically, I don't know, so omega, so lambda and omega are inside, say, some cotangent bundle, or more generally, you think about some exact symplectic manifold where you locally think about it as a cotangent bundle and then build this beast. Okay, so I want to sort of have some analogies, just to kind of have you have a sense of what I'm aiming for here. Okay, so here are some kind of analogies just to keep in mind. So, A-branes, or Lagrangian A-branes, have two versions. There's what you could call the infinitesimal or compact, I don't know, maybe that's a bad word, Fukaya category. And then there's the wrapped or transverse Fukaya category. Okay, so these words represent their relationship to the skeleton. Okay. Similarly, if I give you B-branes, I can think of two natural things. One of them is, say, perfect complexes with proper support, and the other is coherent complexes. Okay? Okay, and of course, kind of classically, kind of a classical thing to have in mind that parallels both of these is, you can think of, I don't know, homology or cohomology. That's right. I don't know, topology. So you're trying to do topology, and there are two things you can assign. You can assign, compactly supported cohomology or Borel-Moore homology. Okay, and going from this here to here is, from the perspective of field theory, is like passive. It's not like there are theorems that tell you it has something to do with taking optional homology. Okay, so what I want to do is I want to give you how to think about this guy in these terms. Okay. Okay, so for microlocal sheaves, there are two natural finiteness conditions. Okay, the one that goes hand in hand with this kind of infinitesimal or perfect with proper support branes is what I would call traditional microlocal sheaves. And which I'll now denote without the diamond. Okay, so let me tell you what I'm going to impose to get this finiteness. Okay? Let's go all the way back to my definition of singular support. Okay, so when I defined singular support, I told you I asked whether a certain measurement was 0 or not. Okay? I can ask for that measurement to be finite dimensional. It to be perfect. Okay? So these are characterized by the microstalks are perfect. So of course I'm running out of time, and that's why I'm going fast. But okay, so if we go back all the way to the beginning, a certain example of microstalk is just stalk. So when people usually talk about sheaves, they ask that a sheaf's stalks are some kind of, at least maybe perfect complexes, bounded and finite dimensional. Okay? So this is a kind of symplectic version. Okay? Now, the other notion of finiteness, which is wrapped, and which we can write as this, is not that these are finite dimensional, but that they represent or co-represent these functors. Okay? So we can ask that these objects co-represent the microstars. Okay? So, okay, yeah, I'm running out of time, so I'm just going to kind of hopefully whet your appetite if you're interested in this kind of thing.
What does that mean?
Yeah, so what it means is, let's go back to like, a picture like this. So here's my cotangent bundle. Okay, and here's my Lagrangian. Okay, let me actually like erase this part. Okay, so here's an example. Okay, now I look at a microlocal sheaf supported on this lambda, and suppose you ask me, does it have singular support here? Okay, so this is some point xc. So what did I tell you to do? I told you choose a ball. Choose a small neighborhood. Okay, here's the ball that is the projection of the neighborhood. And then choose a function whose differential is this. Okay, so in other words, you can take the graph of that function and you can get a small Lagrangian transverse to lambda. Okay? And associated to this little transverse graph of some df, there's a measurement which has probably long since been erased, which was called the test for singular support. Okay? So what I'm telling you is you can do all these tests, okay, and you get functors to vector spaces. Or you can ask, is such a test represented by some object? Okay, so is this equal to the microstalk at some point? Okay? And what I propose is wrap microlocal sheaves is the objects co-representing these restrictions.
Is this wrap category the co-completion of the traditional category?
Yeah, so now there's like a whole list of theorems that you can prove. So these guys actually turn out, so lemma, these guys are the compact objects. So the theory of microlocal sheaves is kind of wrong from the start in some sense. So the theory of traditional microlocal sheaves is wrong in that you are picking out a category that's not the compact objects. You're picking out a small category that's not the compact objects. The right compact objects are these. Okay, so microlocal sheaves are actually in the coherent sheaves, not quasi-coherent sheaves. So I kind of did a bait and switch here in that I really should have written some sort of incoherent. Okay, let me tell you one theorem, and then quit. So there are many, many formal properties that wrap microlocal sheaves satisfy. They're a co-sheaf. There's all sorts of good calculations. You can prove mirror symmetry for pairs of pants, and so on and so on. Let me tell you one thing that just confirms that these kind of analogies are sensible. And then I'll quit. So you can prove the following theorem. Okay, so theorem. Okay, we can look at traditional microlocal sheaves. Okay, so lambda and omega are as we've had them. So lambda and omega are inside some cotangent bundle. Okay, and I look at microlocal sheaves on omega. So it's sections of some sheaf on omega, on lambda. And now there's a natural map to functors from wrapped microlocal sheaves to K-mod, finitely generated K-mod. Okay, so these are exact functors. Okay? And there's a natural functor which is sort of built into the definition, so to speak. I made the definition so that if you take an object whose microlocal stalks are finite, okay, and you eat an object who co-represents a microlocal stalk, out comes a finite dimensional vector space. Okay? Maybe I should put op here. Maybe. Okay, there's an op somewhere in this statement, but I can't parse at the board. Is that correct?
Yes.
Okay, great. Okay, and now the theorem is that this is an equivalency. Okay? So, this is something, of course, that's expected for these guys. Okay? It's something that's true for these guys. Okay, so I'm happy to advertise a paper I wrote with David Ben-Zvi and Toldi Pregel that proves the duality here. This is classical. So in any case, it's true here, and I'm not going to write anything, but let me just say a word about how to prove this, because I think it's a nice piece of technology. I mean, it's a nice application of some technology. So in general, these categories are extremely complicated, but what you can do is you can check that this statement is local, meaning this side is naturally a co-sheaf, and this side is naturally a sheaf, and so somehow it boils down to proving something locally. And then what you can do is you can deform this very complicated lambda to what I mentioned, these guys with arboreal singularities. And on Lagrangians with arboreal singularities, microlocal sheaves are just modules over trees, which are smooth and proper. So the theorem is Poincare duality holds locally on a kind of arboreal Lagrangian. One side is a colimit and one side's a limit, so you have a theorem like this. Okay, so the only reason there's an asymmetry is one side's a colimit and one side's a limit. Locally, everything's smooth and proper. Okay. So the theorem is kind of quite easy once you deform to these kind of arboreal singularities.
Does it follow, so we know that the left side always proper, is the right side always smooth? I mean, wrapped microlocal sheaves, are they always?
I don't know, that's good. I mean, that's not on my list of, I haven't checked that, so I'm not sure.
So there's a map where you switch the two.
Yeah, you can switch the two, but
that's not going to be equivalent.
that's not going to be an equivalence. So the only asymmetry here is that this guy, I mean, without the op, well, anyway, with the op too, but this guy is a co-sheaf, and this guy is a sheaf. So this guy's calculated as a limit, this guy's calculated as a colimit. So a good intro analysis problem is to check that distributions and functions, you know, there's an asymmetry in their duality based on which one's a limit and which one's a colimit. But I want to emphasize, that's the only asymmetry. Once you go locally enough to kind of arboreal singularities, you're just talking about modules over trees, which are smooth and proper. So coherent and perfect are kind of the same. I mean, wrapped and unwrapped are the same.
Does it say locally that they're perfect complexes?
Locally, if you have a Lagrangian like this guy, okay? So if you study this guy, if you look really close at any piece here, you'll just look like you have modules over a tree, and you won't be able to tell the difference between wrapped and infinitesimal. But as you go over the whole thing, one will be a limit and one will be a colimit. Okay? And those two will be calculated differently. They formally satisfy, I mean, the theorem is really just a kind of a formal statement once one knows that you can deform to these arboreal things. Okay, so I'm going to stop just because I'm sort of already over, but let me just say what I would have told you in the third part of the talk is I would have explained how to calculate wrapped microlocal sheaves on the pair of pants and see the mirror symmetry. But anyway, that's another time. Okay, thanks very much.
Very basic question.
Great.
So, you know, so the basic computation of fractal homology is that the fractal homology of the fiber with itself
Yes.
is you know, homology of the
Great.
base group space.
Yes.
So I'm assuming that the fiber here is the,
Yeah.
the
So-
point sheaf.
That's right. The fiber is the, I mean, the dictionary.
So hold on, yes,
Yeah, oh,
so
sorry.
how does home of the coin sheaf know that what the base group space is?
I mean, this is something you know from homotopy theory. If you map a point in, it's not a fibration, but it doesn't obstruct a homotopy theorist from saying that the Hom from that point to itself is the base loop space.
Yeah, the homotopy theorist isn't trying to be local over the base.
Right, exactly.
Co-sheaf.
Sorry, but the point is that as soon as you know that your theory is a co-sheaf, it follows.
It's local in the sense of Van Kempen's theorem, right? Not in the sense of Meyer-Vietoris, right?
I don't know,
Well,
that sounds great.
when you started defining sheaf theory, it was like ordinary sheaf theory.
No, so let's do an example. I mean, just, I don't know, let's do like, you know, well, cotangent bundle of, pick your favorite S1, I don't know, it doesn't matter. I mean, just any base manifold, okay? Let's look at mu sheaf, sorry, I just need to write something. So let's do, this is not an example of this, well, I guess it is, but anyway, example, let's take, you know, again, x equals S1 and d star x equals this picture. And now let's do what you're asking for, let's just take lambda for the zero section, okay? So what is, let's think about what our mu sheaf diamond lambda the global thing here, okay? So what the global thing are complexes of sheaves on the base, okay, whose singular support lies in lambda. So that essentially means they have parallel transport. Okay, there's no singularities. So this guy is what you would call DG local systems, I mean arbitrary local systems on X.
Could you give a very complicated answer? What's a very simple question?
Oh.
If in standard sheaf theory, I just
Yes.
take the sheaf supported at a point.
Oh, but that guy is not in this category.
Yeah, but I didn't ask about this category.
Uh-huh.
You know, take the sheaf that's the point sheaf.
Yes,
And I take Holmes from it to itself.
yes.
To get the homology of the base groups.
No.
Then why
Okay.
do I get it in your place?
Because you're doing a calculation in a different category.
That's the.
You asked for a Hom in the category of all sheaves. I'm giving you the Hom in the category of sheaves with this prescribed singular support. So when you map that sheaf into my
But
category,
isn't that a full subcategory of full sheaf?
yeah, that's right, but your sheaf doesn't lie in that full subcategory. Your sheaf's out here.
I didn't ask for that one that you wrote down.
Oh, well, I mean,
I asked, how does the point sheaf know about the base group space?
it doesn't.
But then,
Can I make a
It
comment?
doesn't.
but the Holmes from the point sheaf to itself are supposed to be,
In this category.
So the point is
but
not,
it's not in this category.
Yeah, but
But it represents an object in this category. So I mean, this matches up exactly with wrapped. I mean, this is your picture, so I don't know. I mean,
It's just saying
How-
the
how do you-
cotangent part generates, right? It's just saying the cotangent part, you can express the zero section.
but Paul wants like
You know,
the
but
Paul
I
wants
know
to
how
see
to
it.
So
make
let me go slowly. Let me go slowly.
fancy
So,
words,
okay.
but, you know,
Let me go slowly so you see. All right. So this category, you're right, is a full subcategory of like all sheaves on X. No, I don't know, like whatever. No restraint at all. Okay. Oh, sorry. No, the point is it's. Sorry.
Paul, I think you also want to bear in mind the analogy to Mohammed's latest universal
Yep.
local system.
I know what I could bear in mind. I just started with ordinary sheaves, right?
But potentially of infinite
So yeah.
rank.
So this is a full. I don't know. Full subcategory.
Yes.
Okay. Now into the room walks your guy, which is I don't know, skyscraper at this point.
Yes.
Okay. K sub P. Okay. So K sub P is here.
Yes,
Okay. He's not here.
yes.
Okay, so you're right. There's a calculation. Hom K sub P in here. Let's be sorry to be pedantic about this. The Hom sheaves on X diamond of KP itself equals K. Agreed. Okay. Now, this full subcategory has a left adjoint. I mean, this full embedding has a left adjoint called wrapping. Okay. So there's a left adjoint here. I don't know. L, okay, which you should morally think of as wrapping, okay? And of course, how is it understood? Well, you know, if I give you a local system, then let's call the local system L, then Hom I'm just going to write down the diagram for an adjunction. Sorry, I don't know. So Hom from what are we calling this? KP to L equals Hom from this wrapped guy. U sheaf diamond lambda X, sorry, diamond became a triangle, to L. Okay? So that's the sense in which I consider this guy to be an object of this category. I can always, you know,
Okay.
do it like
That's
this.
what I was asking.
Yeah. And this left adjoint is very global because if you start with something that you can't propagate in sections and you insist that you can, then you're going to have to keep going around the circle, around and around. You know, you're forcing that the propagation must happen.
you know, like in the symplectic geometry, wrap means you do something when you flow.
Yeah. I'm claiming that there's two types of wrapped, and there's just the left and the right adjoint to this inclusion. I mean, under the dictionary between.
Maybe I try and finish the question.
Sorry.
So, I can apply, as you mentioned in the beginning, contact isotopy or contact dimorphism act on the sheaf category.
Yes.
So I could define wrap sheaves as in symplectic geometry by saying you act by the contact dimorphism rate flow and take a limit.
You have to be much more careful. I mean, no. I mean, but no. I don't think you're applying that in the right way. I mean, I think I think when you say there's this contact morphism, I mean your sheaves in that picture are supported on the fixed points of the contact. I mean, if you do the wrapping, you're like fixing the Lagrangian. All right,
Oh, okay, I can ask you after.
yeah, I think that's not the right picture for this wrapping.
Okay, I'll maybe we discuss it after.
Great.
Okay, we should stop here.
Oh, wait,
sorry.
sorry.
So this seems to say that in your category, you have a much more compact object always.
Mhm.
And that's something better than Lagrangian fair theory, because in Lagrangian fair theory, it may be a case that there is no compact Lagrangian manifold.
That's right.
So my question is that how much simple geometric information this sheaf cohomology has. For example, you have some singular Lagrangian manifold,
Yes.
and you may regard it as an object of this compact
Yes.
microlocal sheaf. For its automorphism is non-trivial.
Yes.
Do you think it implies that this singular thing is non-displaceable?
Yes. I don't know of every instance I know where anyone has calculated the relationship between microlocal sheaves and exact Floer theory. They're the same.
Yeah, but
So,
I mean, you
I don't
can
know
just forget that Floer theory. Suppose
Yes.
you have two compact microlocal sheaf.
Oh yeah.
Suppose it's disjoint.
Yes.
The morphism is zero. Right?
Yeah, that you can, like the kind of technology Vivek is mentioning, that's right, that there's like, all of this is invariant under isotopies. So if you do imply, if you can displace, then you would get something. That's right. Yeah, I mean, this is just an alternative language. I mean, it's not, I don't,
Yeah.
It's not clear that a priori that what we would call a singular Lagrangian actually supports.
oh, in fact, one of the deepest problems in the subject is you give me a singular Lagrangian, like, and you say, okay, here's my support. What's the category? I mean, like, does it carry any objects?
Yeah, but at least you have a lot of objects.
Oh, I mean, here you have a lot of objects because,
non-displaceable, right?
that's right, that's right,
And the support is always Lagrangian, right? Kind of thing.
that's right, that's right.
I see.
Yeah, the support is always, I mean, you sort of are forced into the conic game, but then there's some standard trick you play, you go to the symplectification of the conic. I mean, so the conic is not so important.
So locally, when you chose these omegas, you defined microlocal diamond. It's essentially a localization. You inverted those things.
Yes.
Those morphisms with cones are sheaves without support
Yeah.
in your prescribed region. So because you have a fully faithful right adjoint to capital L for localization, is capital L also localizing with respect to maps that, maps whose cones are sheaves without support in that region?
Yeah, I think that's, I mean, I don't have any feel for the geometry of that statement, but I can say that I think formally, a fully faithful embedding in some nice contexts means essentially that you have a left adjoint with a composition being a projector or something like that.
Just the right adjoint is localization, but left adjoint is just
Yeah, so there's some, I think,
effective subcategory.
Right.
I don't have any kind of geometry to say about it, but I think that's a kind of formal stage.
May I ask another kind of philosophical question?
Great.
So in a Lagrangian case, there is not yet done, but kind of expected that you have a lot of higher genus or higher loop contributions
Yeah.
from the homologue. Do you think that there is something parallel in this world of microlocacy?
I really think of this as being just another view on the A model. So if you tell me that those higher genus contributions are a part of the A model, I would say they're it. So, I mean, I don't know yet how to extract them. I mean, like here I can construct for you many smooth and proper categories. Now, I don't know.
In a B model, there is something similar, right? There's some column of chance and that thing.
Right.
Doesn't Costello tell you?
So the remark is the moduli space of objects in this category carries naturally a shifted symplectic structure, which you can quantize. And that should correspond to what you asked.
Okay, I would suggest that at this point we thank David again. And